Uh, 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 uh. Okay, let's get started. So we are learning about the virtual memory. So this is the another important topic in the memory hierarchy or memory systems. Okay, so actually in the previous class, I briefly introduced about the virtual memory concept. Okay, so as I mentioned, the virtual memory, actually the original virtual memory was designed for small memory space. So it means that, the DRAM is was very expensive. Okay. And then also the size of DRAM was very small. So idea is that, so we can use the DRAM space as the cache, and we can use the large storage space as the data space. Okay, so main idea, the original idea is that, so you can use the main memory as the cache. Okay, cache for storage. Okay, so in order to support the this purpose, okay, then we can access, so uh, the computer system provides the larger virtual memory space, to process. Okay, the process is the launched binaries, right? So actually, this is the launched process. Okay, and then actually the operating system provides the larger virtual memory space. This is the virtual memory. But I mentioned that the virtual memory is a fake memory, right? It's not real. Okay, so the virtual means it's fake, right? So actually, when we execute the load instruction or store instruction, then I mentioned that this address is the virtual address. Okay, and then actually, in order to access the real data in memory or storage, okay? So data can exist in the main memory, so it means the physical main memory or storage space, okay? So then in order to access some real data in physical memory, then virtual address needs to be translated into the physical address, right? And then using this physical address, that we can access the real data in physical memory. I mentioned that physical means real, right? Real in computer systems. Okay, but I also mentioned that, so currently the main memory is also very large. The size of a main memory is very large, but the virtual memory is a very convenient concept for programmers. Okay, I mentioned that programmers do not need to consider the configuration of real physical memory or the configuration of real computer systems. So this is because the operating system just provides the very large virtual memory space. And then this virtual memory space is just assigned to a single process. Okay, so when our programmers write a code, the programmers do not need to consider the other processes that share the memory systems. So actually when we run our computer systems, many processes share the memory resources, right? So you can check the launched processes on Windows or Linux operating systems, right? But it means that the many processes need to share the physical memory space, but operating system just provides the single virtual memory space to a process. So process can just access this single virtual memory space, but this virtual address needs to be translated into the real physical memory space, right? So this is the concept. So programs. So programs mean the launched processes. Programs share actually main memory, right? So which means that actually the programmers need to consider this situation, right? So the main memory is shared by multiple processes, but actually the programmers do not need to consider about this situation, right? So actually the virtual memory, the virtual address is just translated by operating systems and memory management unit in CPU. The memory management unit is the hardware support for this virtual memory, okay? And then operating system just provides the virtual memory space, okay? So CPU and OS, operating system, translate virtual addresses to physical addresses, okay? Okay, let's see the concept. So you can see this figure. So you can find that this is the virtual addresses. This is the virtual memory space provided to the launched process. And then, so this is the physical address. The physical address in the real memory, real physical memory. So which means it's DRAM address. Also, you can find that this disk addresses, so hard disk drives or the SSD, the solid state drives. So actually, the operating system provides this amount of virtual memory space, right? And then as you can see, actually the physical memory space is smaller than this virtual memory space, right? So which means some data in virtual memory space can exist in the physical address, the physical memory space, or the some data in virtual memory space can exist in disk. So this is actually the swap space in a disk, the hard disk drives or the solid state drives, right? So, so this address needs to be translated into some physical address in real memory, right? So in order to support the virtual memory concept, then the virtual address needs to be translated into the physical address. And then this is the translation concept of the virtual address to physical address. So we know that actually the address in computer systems is byte address. So what does it mean? It's the one byte occupies the address 1, right? But think about this. So, but if we just translate the all byte addresses, then the overhead will be very large. So think like this. So the 1 is translated to 1000, 2 is translated to 1001, 3 is translated to 1010. So actually, in order to translate this address, then we require translation table, right? So for OS or hardware needs to support the translation table, right? But which means that actually we require very large amount of the translation entries, okay, in order to the byte address to the byte address of the DRAM address. So it's not good. So the overhead is very high. So actually, so when the virtual address is translated, so the LSB, the lower 12 bit. So you can find the bit number 11 to 0 here, right? So lower 12 bit of virtual address is not translated. It's just copied to the physical address, right? And then the upper bits are translated into the physical address. So if you see that this figure, so you can find that the lower 12 bit is lower 12 bits of virtual address are just copied, and then the upper bits are just translated. Okay, so because the lower bits are bit number 11 to 0, so there are 12 bits. So the size of this part is the 4 kilobyte. So when the virtual address is translated, then the virtual address is translated into the physical address in a granularity of 4 kilobyte. Okay? And then this 4 kilobyte size is called the page. Okay? So this 4 kilobyte of size is called a page. Okay? And then only the upper part of the virtual address is translated into the physical address. So this upper part is called the virtual page number, and then it's called the VPN, virtual page number. And then, so this part needs to be translated into the physical address part, and then this upper 12-bit physical address part is called a physical page number. So it's a PPN, the physical page number. And then the lower 12-bit part is called a page offset. Okay. So this is some translation rule. And then recently, then this physical offset size can be changed by operating system, but usually the operating system sets the fixed size of this page offset. Okay, like 4 kilobyte. So 4 kilobyte of page offset. Okay, let's see the example. So this is the virtual memory space, and then this is the physical memory space. Okay, and then let us assume that the virtual page numbers virtual page numbers occupy 19 bits of the virtual address, and then physical page number occupies the 15 bits of physical page number. Okay, so and then 12 bit. Where is the 12 bit is the lower 12 bit is the page offset. Okay, so you can find the virtual page number here, right? So like from 0 to 1111, and then you can also find the range of each page. So because the page offset occupies the 12 bits of the virtual address. So this is the 3-digit in hexadecimal number, right? It's a hexadecimal. So you can find that address 002 FFF is allocated to the virtual page number 0000, okay? 0002 FFF, so 12 bit. So this amount of block, so this is called a page. This page has the virtual page number 000. So in this example, the virtual page number 002 is translated into the physical page number 7FFF. So you can find the address range. So this is the virtual address range. So 20002 2FFF is translated into the 7FFF000 and 7FFF. So because the physical page number is 7FFF. Okay, so this is the example. What is the physical address of virtual address 247C? You know, this is the hexadecimal number. So what is the page offset part? Page offset part of this address. So because this is the hexadecimal number, so we can select the 3-digit, right? Because 1 digit of a hexadecimal number is equivalent to the 4 bits, right? And then I mentioned that the page offset size is 12 bit. So which is the 3 digits in hexadecimal number. So this is the page offset part. Then the virtual page number is 2, right? So where is the 2? So virtual page number 2 is here, and then you can find that, oh, the virtual page number 2 is translated into the physical page number 7FFF, right? So the upper part of the physical address is the 7FFF. Then what is the page offset? Page offset is the 47C, the lower 12 part. So I mentioned that the page offset is just copied. Okay, we don't need to translate the page offset part. So it's 47C. So physical address is the 7FFF47C. So what does that mean? When the load word execute so it's a x1 and then some address. So this is the address. Then if this address is 0x247C, then actually this load word access the physical address 7FFF47C. Right? So it needs to be translated. And then another, so wait, where is it? Oh. Okay. So this is the translation example. Okay. And then, so it means, so I mentioned that the virtual memory space is larger, so larger than the physical memory space. And then which means that some data, actually some pages are not mapped to the physical memory space. So some pages need to be mapped to the storage. Okay. So storage space. So which means, so it looks like this. Actually, you know, the storage systems are managed by operating systems, right? So it is because the storage systems are very, very slow, and then storage systems are connected to the computer system, CPU, via input and output interface, the I/O interfaces. So, and then actually recently we use NVMe. So it's some storage protocol works on the PCIe, so very fast interconnection network. But actually the operating system manages the data transfer between CPU, actually the main memory and storage. So what does that mean? So actually, when a page, the target page exists in the storage, then actually the the virtual page number is not translated into the physical page number. So it is because the physical address is the address of the RAM. And then I mentioned that the storage is managed by operating system. Okay, so which means when a virtual page number is translated to the data in storage, but actually the mapping information cannot be found in this data structure. Okay, so and then this situation is called the page fault. Okay, it's a page fault. So page fault represent using the load word, like, and then so virtual address needs to be translated into the physical address, but the target page exists in the storage. Okay, so we cannot get physical address in this case. So this situation is called page fault. Okay, so and then for this page fault situation, then operating system needs to fetch, which means needs to read page data from storage and then transfer this page data into main memory. Okay, this is a page fault, and then operating system needs to handle page fault situation. So that's actually, in the homework number 4, I mentioned there is a page fault in the data cache, right? So this is this situation, right? It's a kind of exception, right? So actually, and when you access the storage system, it will take a very long time. So it is because the storage is very, very slow, and then also storage accesses are managed by operating system, which means software, not hardware. Okay, software manages the data accesses to storage. It's very, very slow. Okay, so it's handled by operating system code. Okay, so I mentioned that the page fault is kind of exceptions. Okay, so it's handled by software. So, and then in order to improve the performance of our computer system, so we need to minimize these page faults, right? Because it will take a very long time. Okay, so so I will explain later. So actually, I already explained that this. Okay, so and then I will explain how the virtual page numbers are translated into physical pages. So actually, the virtual memory. So maybe this is. I think this part is a little bit tricky. So it is because actually as I mentioned, the virtual memory is managed by both software and hardware. I mean, the hardware and operating systems. So sometimes when I explained about the virtual memory concept, then it includes the software part. Also, also the virtual memory concept includes the hardware part. Okay. So I will explain how this mapping information is managed. So actually, so this is the concept. So the virtual address needs to be translated into the physical address. So I just explained the concept of the address translation. And actually, the hardware and software, software needs to support this virtual memory concept. So, the operating system. When I mention software, it represents the operating systems, right? So, actually, we learned that when a virtual address is translated into physical address, actually, which means that the virtual page number, the upper bit, the virtual page number needs to be translated into the physical page number, right? And then for this translation, we require mapping information. Right. So like this is the virtual page number 1, and then this virtual page number needs to be physical page number 0x FFF, something like, and then 2, then it says the 0x 10F, something like that. So how can we support this translation? Actually, this information is managed by operating system. And then actually, when an operating system launches a process, the virtual memory space is created by operating system, and this, which means actually the page table. So this mapping information is managed by page table. So page table is assigned to the launched process. And then using this page table, this mapping information is provided. Okay. So, so it looks like this. So, so page table is the array, right? And then this page table includes some information, right? So it's a mapping information like the physical page number. Then what is the index? What is the index of this page table? Index is the virtual page number. So when a process is launched in a computer system, operating system creates the page table. This is the data structure. Actually, array. This is the array structure that includes the physical page number. Okay. And then if the virtual page number is given to this page table, and then we can use this virtual page number as the index of page table, right? Then we can access the corresponding entry, in the page table, and then we can get the physical page number. Okay. And then this operation is supported by operating system. Okay, so this is data structure, right? It's a data structure. And then, so which means this data structure actually exists in the memory. It's a main memory. Okay. So you may be so this concept is a little bit tricky, as I mentioned, because actually the operating system also manages this virtual memory support. Also, the hardware also supports this virtual memory concept. Okay, so it looks like this. So when a process is launched in a CPU, then the pointer of the page table, okay, is a page table 0, the base address. The base address of page table is stored in the page table register, right? So, and then when the load word is executed, and then I mentioned that this load word uses the virtual address, right? So then the virtual address is given. So this is the virtual address space. And then I mentioned that the page offset is not translated. So lower 12 bits of virtual address is not translated. Only the upper part, virtual page number part is translated. So using the virtual page number, like a BPN, then we just access the page table and then BPN. Okay, so this means this is the index. The BPN is used as the index of page table. And then, so this is the page table, the structure of page table, but I mentioned that the base address is stored in the page table register. So using the base address and the BPN, we can access the entry, the corresponding entry, okay, like here. And then this entry includes the valid bit and physical page number. So valid bit represent, this physical page number is valid or not. So if it means if the physical page number is valid, which means the page exists in main memory. Okay, because the PPN is valid. If this flag bit is invalid, so this is the page fault case, which means the target page exists in storage system, storage. Okay, so it's a page fault. Okay, so if we access this page table, so as I mentioned, this structure, this array, this structure is called a page table. So then we can get the PPN, the physical page number. So by combining page offset and then physical page number, we can get the real physical address. This is how the virtual memory, so virtual memory translation works in computer systems. Okay. So actually this entry includes the additional control bits, but in this example, I just showed the valid bit only. Okay, so if the valid bit is 1, so which means that the target page exists in the physical memory, like a DRAM. Okay, and then if the valid bit is 0, which is invalid, so which means that the target page exists in storage. Okay, so let's see the example. So this is the page table example, and then what is the physical address of virtual address 5F20? Okay, so because the page offset is 4 kilobyte and then 12 bit, the lower 12 bit, this part is the page offset, and then this part is the virtual page number, right? So you can find the PPN is 5. And then this is the page table. And we can find the target entry using the virtual page number. So it's like it's a page table, and then it's a 5, right? So indexed by the virtual page number. So if we read the this data, then we can find that, oh, the valid bit is 1. So which means that the target page exists in DRAM, main memory, right? And then what is the physical page number? Physical page number is 1. Okay. So VPN is just translated into the physical page number. So 5 is translated into the 1, right? So physical address becomes the 1F20. And then using this physical address, we can access the DRAM. Okay, so this shows how the virtual address is translated into the physical address by page table. Okay. Another example. What is the physical address of a virtual address 73E4? So like the same way, so the lower 3 digits of a hexadecimal number is the page offset. So this is the page offset. And then the VPN is 7. So we can check the PF, the virtual page, and then indexed by 7. So then, the valid bit is 1. No, 0, 0. The valid bit is 0. So entry 7 is invalid. So which means the target page exists in storage. So it's the page fault. It's page fault. And then this is a kind of exception. So which means, load word is executed by CPU, right? And then the virtual address is translated by the physical page. But we found that the valid bit from the page table is 0. So this is the page fault, and then this is an exception. Okay, and the exception needs to be handled by operating system, right? So this page is fetched from the storage, and then this page is stored in the physical memory, so like DRAM. So which means it's not explained. Okay, so if the page fault is detected, then the page data is read from the storage. Okay, and then this page is stored in the DRAM. What does that mean? Now we can get the address of this page, right? Right? So address is, so the address of this space is just stored in the page table, like the 1, 2, 3, 4, okay? And then operating system changed the valid bit of this entry as 1. And the load instruction is executed again. So that's what I explained in the exception part, right? So when the exception is detected by CPU, then this instruction, like load instruction, the load instruction is flushed, is cancelled, and the operating system, actually the CPU calls the exception handler. So it's the page fault handler in operating system. And then the operating system, the page fault handler calls are executed. After that, load word is fetched again, and then it's executed. Right? So in this case, Oh, page table is updated, right? So it's a valid. So we can read data from physical memory. So that's how the page fault is handled by CPU. Okay. So, okay, so this is the summary of the mapping. So, okay, some pages can be mapped to the physical memory, and then also some pages can be mapped to the disk storage. So storage system, actually the swap space, our storage system. Okay, so the concept of this virtual memory is similar to the cache, right? So it means actually we can store frequently used pages. Okay, so actually the virtual memory is managed granularity of a page, right? So which means when we manage virtual memory, then frequently used page needs to be in the main memory, right? To improve the performance of a computer system, then the main memory is faster than the storage, right? So which means that the frequently used data needs to exist in the main memory, obviously, right? Then how can we manage these pages? Okay, so actually, we can use the LRU replacement, right? Like so. So we learned about the LRU, the least recently used policy in cache, right? So we can also manage the pages like LRU, right? But it's very expensive. Okay, so the operating system just manages this page table like this, like the reference bit in the page table. So if the page table, a certain entry of a page table is accessed, the operating system just set the reference bit as 1. Okay, then the operating system periodically clears this bit like 0. And then when the replacement is required, the operating system just use the page which the which uh, whose the reference bit is 0. Okay, then they just randomly selected. Okay, this is some management scheme of the page table. Also the write operation. So also the storage system is very, very slow. So we also need to use the write back policy. Okay, so which means the page table entry also includes the dirty bit. Okay, so like the cache, so the write back cache includes the dirty bit, right? So page table also includes the dirty bit. So actually, as I mentioned, the page table entry includes the many control bits, many control flags, right? It is because the security is also managed by these page tables, right? Also the read write permission or some so it's a like dirty bit. these flag with these control bits also stored in the page table entry. Okay. Okay. So we learned about the page table, and then we learned how the virtual address is translated into the physical address. Then what's the problem? So I mentioned that the page table is the data structure. So actually this is the array. Okay, it's a data structure. And then I explained that, oh, load word is executed. Like load word A, that is the address, but this is the virtual address, right? So in order to access the data, it's a load. What? What's the Oh, sorry about that. What happened? Okay, it's terminated. Okay, okay. Sorry about that. Okay, it's working. Sorry about that. So the problem is that when the load order is executed by CPU, then we learned that this is the virtual address, right? So which means that in order to access real data, the data in the real memory, then this virtual address needs to be translated into the physical address, right? We learned. So, and then for this translation, actually we need to access the page table. So which means the page table array. So it's an array. So it's a real data, right? It's an array it's the array data. So what does that mean? This data is also in the memory. What does that mean? Actually, we assume that in order to execute this load instruction, we expect that only one memory access is required, right? That's what we expected, right? But actually, in order to access this data using the virtual address, firstly, the virtual address needs to be translated into the physical address. So what does that mean? Actually, the CPU needs to access this array, the page table, and then CPU needs to get physical page number. So problem is that actually additional memory access is required. Do you understand? Actually, so this is the load instruction. Load instruction executed by CPU, but the virtual address needs to be translated into the physical address. And then for this translation, then CPU needs to access the page table. And where is the page table? You know, the page table is data structure. It's like array. So this is also data. Where is this data? In the memory, right? Problem is, so we expect, the only one load instruction, only one memory access is required for this load instruction. But actually, in order to execute this load instruction, we also need to access the memory. So actually, two memory accesses are required. And then we learned that the memory is much slower than the CPU, right? So performance overhead. Performance overhead is the disadvantage of this virtual memory concept. So how can you solve? The problem, it requires the multiple memory accesses. And then the problem, memory is slow. So how can you solve this problem? So we learned, so in this chapter, because the memory is slow, we solved this problem using cache, right? It's cache. So what is required? If this information, the the mapping information, if this mapping information is also cached in a CPU, then we can quickly access this mapping information, right? Right? So if we just access this page table, the page table in a memory, then we require the memory access. But I mentioned that the memory is very slow, right? So how can we handle these issues? This issue using cache. But what will be? What is cached? What needs to be cached? Mapping information. This mapping information can be cached in a CPU. Then we don't need to access memory. So we handle the slow memory issues using cache, right? So which means, if this process is slow, then we can also use the cache. So in order to access the page table, so this is the problem. So the page table entry is called the PTE, so it's a page table entry. Okay. So actually the virtual memory concept requires the extra memory accesses. So this is the problem. So in order to avoid this memory accesses, we can cache. We can cache what? Page table entry. Okay, so I mentioned that this is the page table. Okay, then some entries can be cached in a CPU. Okay, like this data can be cached. Then we can access the this cache. So CPU manages this cache separately because this translation is very critical. That is very critical for the performance of a computer system. So this special cache is called the TLB. It's called the translation leukocyte buffer, TLB. Okay. So this is the special cache for page table. So it's a separated cache. So we learned about the cache hierarchy, right? But this cache hierarchy is used for data, the normal data. But for the virtual memory, actually the CPU includes the special cache. So special cache for page table, the page table entries. Okay, and then this cache is called TLB, the translation leukocyte buffer. So if you read the CPU specification, you can also find the TLB configuration. Okay, so TLB is used as the cache for the page table, and then so actually the TLB miss rate is very low. So it is because actually the data chunk size of the page size is 4 kilobyte. So which means that, and then we learned about the spatial locality, right? So because of spatial locality, when some translation, the PTE, when a single PTE is accessed, and then because of spatial locality, then same PTE, same page table entry will be accessed again and again and again, right? Because of spatial locality. So if this single page, so this page table entry is cached, so stored in a CPU, then this mapping information can be used again and again and again and again. So this is a very good idea. So we can just cache the page mapping information in TLB, and then using this cache, we can quickly access the page table information, the mapping information in TLB. So the miss rate is very low. Okay. So the structure, but the structure is so it's more complex, right? Because of TLB. But you can think that this TLB is the cache, just the specialized cache for the page table. Okay. So load word A. So this is the virtual address, right? Then using the virtual page number, then we can firstly access the TLB. Okay. Then TLB includes some page table information, right? So page table information includes the physical page number and then some flags, right? So these informations are data part of TLB. Then because the TLB is the cache, we also need to store the tag. Okay. So when we, so when we learned about the cache, then we also need to store tag because the cache size is smaller than the main memory, right? TLB is the same. TLB size is smaller than the page table. We also need to store tag. But in this case, we access the TLB using virtual page number, right? So which means the part of virtual page number will be used as the tag. So, the last question of the homework number 4 is related to the TLB, right? So, like the cache, when we access the cache, we use the address, right? But when we access the TLB, we need to use the VPN, the virtual page number. So the upper part of the VPN is used as the tag, right? So using the VPN, then we firstly access the TLB, and then the tag is compared. The tag is compared with the part of virtual page number. And then if this is valid, and then the tag is matched, then we can read the physical page number and then flags from the TLB. Then we can quickly perform the address translation because we can just access the TLB. And TLB is also very fast because it is inside of a CPU. Also, the size is very small. But we can encounter TLB misses, right? So this is the TLB hit case. Okay, the VPN is found in the TLB. But for the TLB miss cases, we need to access the page table, right? Then this entry, if the page table is valid, then this entry is fetched to the TLB. Okay. And then also this target entry is invalid. Then this is the page fault. Then the page fault is managed by the page fault handler. Okay. So, the operation is a little bit complex. Okay. So, a little bit complex, but this operation is required for increasing the performance of our computer systems. Okay. So TLB is the hardware structure. Like the caches are managed by hardware. So TLB is the same. TLB is the cache of page table, right? It's a specialized cache for page table. So TLB is also managed by hardware, like CPU. Okay. And then page table is managed by operating system, but CPU supports this translation. So like the base address of the page table is stored in the page table register for each process, and then the CPU also supports the access to the page table. But actually, the firstly access the TLB, and then if the TLB miss is encountered, then access the page table in the memory. But actually, this operation is a little bit more complex. The more complex in the real CPU, because so actually this operation is very critical for the performance. So commodity CPUs such as the Intel or AMD CPUs includes the more complex hardware structures for supporting these virtual memories. Okay, virtual memory space or TLB. Okay. Okay, so that's what I explained. Okay, TLB means, and then page fault is also explained. Okay, so now actually we learned about the TLB, but and then I will explain how the cache, it's the real cache, the data cache, how the data cache interact with TLB. So in chapter 4, when we learned about the process architecture, we learned that, oh, this is the instruction memory, and then this is the data memory. But actually, we learned that these instruction memory and data memory are actually instruction cache and data cache, right? And then actually, in order to access when a program is executed, the address in the programs are actually virtual address. Okay, that's what we learned. Okay, and then actually, so which means the virtual address needs to be translated into the physical address. So you need to understand that virtual means fake. So which means if we just access data using virtual address, then it's a fake. We cannot read. We cannot read the real data. So which means we need to translate the virtual address to the physical address, right? And then in order to run CPU, the CPU requires the real data. This is the real hardware, right? What does that mean? All addresses in a program needs to be translated. So actually, before accessing data cache or instruction cache, then first we need to access the TLB and then also TLB. So because there are instruction cache and then there are cache in a CPU, there are two TLBs, instruction TLB and data TLB. Okay, and then before accessing instruction cache, the CPU first accesses TLB and gets the physical address, and then using the physical address, then CPU needs to access the instruction cache or data cache. So like this. So this is the virtual address. So this is virtual page number. And firstly, access the TLB. And then if the TLB hit is encountered, then we can get the physical address. So this is the physical address. Then using this physical address, then we can access the cache. Okay. This is the memory operation. Real memory operation in CPU. Okay. But what's the problem? Performance, right? Because we assume that for the level on cache, we assume we can just consume only one clock to access the level on cache, right? But we learned that actually before accessing level on caches, a CPU needs to access TLB. So this is the hardware. So the CPU will consume additional cycles for accessing TLB. So which means, so actually, in order to access the data caches, level on caches, then we may require additional cycles for accessing TLB. So this is the problem. So which means that heat time can be increased. So in order to reduce the performance overhead, some CPUs may access the level on cache using virtual addresses. So okay, that can be possible. Some CPUs, actually, the modern CPUs employ this mechanism. So it is because actually for the level on cache, we need to reduce the heat time. But because of TLB, the heat time can be increased because we need to also include the TLB access time. Okay, so in order to avoid this performance overhead, the CPU may access the cache using the virtual address, but it also requires additional considerations. Okay, it's because the virtual address is fake. It's just virtual, not real address. Okay, but this is the advanced issues. So it will be covered by advanced computer architecture. Okay, so we can use the page table for the memory protection. So it is because actually the CPU runs the multiple processes, and then these multiple processes share the physical memory. Okay, and then we frequently use the shared libraries also. Okay, so some data can be shared by the multiple processes. So which means, oh, the virtual address is different. So because the multiple processes, the virtual addresses can be different. So this is the process 1, process 2, and then actually the virtual address 1 and virtual address 2 can be different. But using the page table, this different virtual address can be mapped to the same physical page. It's a shared data. So by doing this, we can share this data in physical memory. The data can be shared by the multiple processes. Okay, so it's a data sharing. Okay, but operating system also use the protection bit. So which means that some pages need to be isolated for security issue. So the operating system can manage the security of the system like this. Okay. So it's a maybe so if you take the operating system course, then I believe the page this virtual memory, the virtual memory will be also covered again by operating system course. Okay. Okay, so I will skip the cache coherence. Okay, so this is the example. So if you see the CPU specification, so you can find the cache configurations right here. So this is the example of ARM and Intel. So if you can find this information. Okay, also you can find some virtual memory configuration like the virtual address, like ARM is a 48-bit, and then Intel, so it's in use the 48-bit, and then the physical address. So this physical address determines the maximum physical memory size. So what does that mean? ARM, the physical address is the 40-bit. So what is the maximum size? 2 to the 40. So this is the 1 terabyte. Okay. So it's a it's just the maximum size of the memory supported by physical address. Okay, and then also you can find some TLB. So TLB organization, CPU specification. Okay, okay, okay. So we learned about the memory system. So memory system is designed for increasing the performance, and then the memory system performance is very critical for the performance of computer systems. So that's why the memory systems are very, very important and very critical. Okay, so we learned about the cache and then the virtual memory. Okay, so I will conclude this chapter 5. So when I mentioned the chapter 5, this is the chapter of the textbook, and then as I mentioned, so I will record the chapter 6. The chapter 6 is actually chapter 6 includes the Amdahl's law and then some the parallel processing issues. And then Amdahl's law can be included in the final exam. Okay. So I will record this chapter 6, and then I post the chapter 6. Okay. So actually, this is the last class, last in-person class, right? Okay. And then thank you for your attention. And then good luck for the final exam. 감사합니다.